I'm back. Woohoo! We are going to find the moment of inertia of a sphere. Mind-blowing, I know, right? A uniform sphere. Okay, so when we look at this, it's got a radius of r, right? And what do? Well, this is actually a beautiful Calculus 3 problem. So when you're in Calculus 3 or math methods later in life, this is a great Calculus 3 problem. You're going to love it. But when we're in Physics 1, we are going to try to find a different way to solve it. Instead of doing the full three-dimensional integral, we're going to think about our sphere as a collection of disks, right? So we're going to take our sphere and we're going to slice it up into a collection of disks, right? You imagine you take your sphere and you just go and you karate chop the crap out of that thing, right? So that you get kind of like, you know, like French fries, like nice and thin layers of a disk, right? So, and well, we know each one of these is spinning around the axis of rotation, and that's going to be spinning with a moment of inertia of 1/2 mr squared, where the r squared is the radius of the disk. Now, each disk is going to have a different radius, right? Because each little potato French fry, right, has a different radius. This French fry's got a huge radius, whereas that one's got a little baby radius, right? So, the moment of inertia of each of these little French fry disks is 1/2 mr squared. Now, what we got to do is we got to add each one of those up, right? We're going to add each one of these up, right? And we're going to say that our French fry is actually infinitesimally small, right? That it's just a really, 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 really thin disk, right? So, well, whenever I'm adding these things, and I have a sum and I have a little bit of dm there, I stretch my summation sign out, and I turn it into an integral, dm r squared. So now what I need to do is go on that same mission I've been doing all along, is to get m and r related. Once I get them related, then now I can do my integral and find the moment of inertia. All right, so let's take a look at one French fry. So the outer, this distance here is r, right? That's the radius of the sphere, right? So we can imagine you have a sphere here, and this French fry here is really thin disk that goes around like that, right? So it's really thin here, okay? So now, what are we going to do? Well, the first thing that we're going to do is we're going to draw this point here. That's the radius of the circle, right? The radius of the sphere, right? Big R. And this here, this is the little r. That's the radius of the French fry, right? And that's going to change. Up here, it's going to be really small. It's going to get bigger, 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 bigger. And here in the middle, it's going to get maximum, and then it's going to get smaller, 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 until when it gets to the pull down here, it's going to be infinitesimally small. Right, so this radius changes. All right, and then let's complete the picture by saying that there's some distance here, z. So we can already think about a relationship between little r, big R, and z, right? That's a right triangle. So if I look at this, big R squared is equal to z squared plus r squared, right? Pythagorean theorem applied. So if I have an r squared here, well, that's pretty straightforward. I just take this and I solve it for r squared. And you get r squared is equal to big R squared minus z squared. And you plug that baby right in, so that your moment of inertia of your sphere becomes 1/2 the integral of dm times r squared minus the z squared. Okay, but now I got to get dm in terms of the r and the z variable. That is going to be tricky. So let's think about our cylinder and dive in a little bit deeper. So imagine I have a cylinder. It's a disc. Right? It has a certain thickness here. The thickness is going to be dz, right? And the area here is going, the area of this surface, that's going to be pi little r squared. So the volume of the sphere is, the volume of the disk is equal to pi little r squared times dz, right? The area times the thickness. Let's come back to our disk. Let's come back to our sphere. What's uniform, right? Because as I start here at the top, I'm only going to have a little bit of mass in my disk because the little radius at the top, at the northern pole, is 0. But as I go down, my disk gets bigger and bigger and bigger, and the amount of mass that I get, and that becomes proportionally the same. So what's going to happen as it comes back down, it's going to get smaller and smaller and smaller. So if I think about it, a sphere is really a three-dimensional thing. So the only thing I can look at is the density. I know because it's uniform, the mass density rho has to be constant. Whether I'm looking at a little bit of mass, right, or a crap ton. Yeah, big M is a crap ton, or the mass of my ball. Okay, so now what do I know? Well, I know what dV is, right? That's the volume of my disk. It's going to be, so if I plug in here, you get dm over pi r squared dz is equal to the mass over 4/3 pi big R cubed. What is this? This is the volume of a sphere. Right? This is the ratio of the mass to volume of the disk. This is the mass to the volume of the sphere or the ball. Right? Now, it should be pointed out here that this thing here is something that I'm going to allow you guys to write down on your cheat sheets for the exam. You can write down the volume and areas of a variety of objects for your exam. This is a great Calculus 3 problem. When I teach math methods, I start by showing that problem and saying, like, by the end of the class, you need to be able to do this, or else, you're not going to pass the class. It's like, you have to know how to do that. But that's at like the sophomore and junior level of physics. For first year physics, so I'm also counting on you too, junior and senior chem and bio majors, we can just write this down. This is a number that we look up. I expect that when you get into Calc 3 or math methods, you're going to become an expert on how to solve that. Okay, so we karate chop and cross multiply again, and we can take that and plug it right back in there for dm. So we get dm is equal to, well, the pi's are going to cancel. You're going to get 3/4 m over r cubed r squared dz. So you take that bad boy and plug it right in there, and you get the moment of inertia of a sphere is 3/4 m over big R cubed times big R squared minus z squared times big R squared minus z squared dz. Now, you might say, well, wait, whoa, 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 whoa. Hold the phone here. What happened? I had an r squared there, right? It's a little r squared. And here I plugged in r squared minus z squared. But if you remember, we did that earlier on by doing Pythagorean theorem on my disk. And I plugged in r squared is equal to big R minus z squared. So when I plugged this back in there, I was just like, bam, done. Right? I didn't have to go through the whole logic again. Right? So if you are interested in logic, just pause the video and go back in time and watch it there. All right, so then now doing the calculus and the math is kind of a shit show, but it's not that bad. So when I see something like this, if I'm in Calc 2, I start thinking like U subs and things like that, but I promise that this actually isn't that bad. You just FOIL it and you do the integral, right? Because there's nothing in the denominator, I don't really have to think too hard when I do this integral. So let's pull out my constants. So I get 3/8 m r cubed, right? And then I have the integral of, and now I just FOIL this bad puppy out. So I get r to the 4th minus 2r squared z squared plus z to the 4th dz. Now there's a really interesting question, right? I remember that this is my sphere, and I'm going to integrate from this point here, where, or maybe from this point where z is minus r. I'm going to keep adding these disks up until I get to the top where z is now r. So when I get a definite integral, I see, well, crap, that's what I should do, right? Where I start with minus r, and where I end is big R. Now, if you're like, whoa, wait a minute, hold on. But you've been like starting in the North Pole. Well, if you start this integral at the North Pole, you go from r to minus r. It will give you the right answer. It will only be negative. And that should send red flags, right? Moment of inertia can't be negative. But I think if you think through it, you'll see, well, wait a minute, if I just started the other way, it works out nicely. Now, again, if you're in Calc 2, you might recognize this as an even function. So you can make the integral significantly easier by taking advantage of that. Let's just do this the tried and true way. If I have the moment of inertia is 3/8 mr cubed, and now I do the integral, you get r to the 4th z minus 2/3 r squared z cubed, right, plus z to the 5th over 5, evaluated from minus r to r. So now everywhere I see a z, I put in the r. So is is equal to 3/8 mr cubed. Hi, John.
How's it going? What are you doing here?
That was John Dewar,
A little video, okay.
professor of the physics department. All right, so I'm going to take this R and plug it in here after I shut the door. So this becomes r to the 4th times r. Then I have minus 2/3 r squared times r cubed plus r to the 5th over 5. And then what I do, right, is I make this minus, And then I plug in the minus r. So I get r to the 4th times minus r minus 2/3 r squared minus r cubed plus minus r to the 5th over 5. Okay. Woo! Now I got a lot of algebra to do. Right, so I'm going to pull it back up to the top here. Okay, so we're going to have IS is equal to 3/8 mr cubed. And now this is going to be r to the 5th minus 2/3 r to the 5th plus 1/5 r to the 5th. Minus a minus is going to be plus r to the 5th. Minus a minus becomes negative 2/3 r to the 5th. A minus times a minus becomes positive 1/5 r to the 5th. Okay? So now we can pull out our r to the 5th, and we get 3/8 mr to the 5th over r cubed. Well, that's going to do something interesting here. It's going to squash that down to r squared. And I'm going to have 1 minus 2/3. Well, I can do some arithmetic right away. 1 plus 1 is 2. Minus 2/3 is minus 4/3. Plus 1/5 is plus 2/5. Cleaning them up a little bit more gives me, I can pull out a 2 here. So I get 3/4 mr squared 1 minus 2/3 plus 1/5. Get a common denominator, which is 15. So IS is equal to 3/4 mr squared. So here for my common denominator I have 15 over 15 minus 10 over 15 plus 3 over 15. Okay, so let's do some arithmetic. 15 minus 10 is 5, plus 3 is 8. So the moment of inertia of a sphere is 3/4 mr squared 8/15. Okay, let's keep going with this. Pull this out. 8 over 4 is 2. 3 over 15 is 5. 2/5 mr squared.